If you need to understand where the Sig Fig rules come from going from concentration to pH, this video will help you. All right. In chapter 1, we had talked about scientific notation, where scientific notation actually comes from, the setup of the mantissa versus the exponent, the power 10. So we are actually going back to that language to understand where Sig Fig rules for pH comes from. Let's say that we have a concentration of 1.03 times 10 to the negative 7 for our hydrogen ion concentration. What does this actually mean? So in the decimal number, we have 0.1, 2, 3, 4, 5, 6, 7 as we reach that value. So there are 7 spots that we had to move that decimal to create that exponent. When we start to convert this, remember the mantissa is showing us the significant digits within this number. So the first sig fig needs to occupy the ones place, and any subsequent sig or significant digit will occupy the decimal spots. So we know we have 1.03 as that mantissa. Then we have to look at what is the power of 10. How many times did we move that decimal, right? And so we moved it 7 times. 1, 2, 3, 4, 5, 6, 7. And when we look at those two values, that's what gives us our scientific notation. All right, so that should be a refresh from where these values come from, how we go from decimal number to scientific notation, and the power of 10 with that scale, that logarithmic scale. So we're in the exponential form right now. All right, so if we have our pH, it's the negative log of that hydrogen ion concentration. So the negative log is the inverse function. So since the exponent is negative, we would get a negative whole number. But by taking the negative log, we get a positive whole number. All right, just to make things easier. So when we take the pH of negative log times 1.03 times 10 to the negative 7, we get 6.987. Where the Sig Fig rules come from, the number of significant digits that are in the scientific notation, or the mantissa. So the number of significant digits in our mantissa is the number of decimal places within the pH. Reason being is the number preceding, the number that is occupying that ones place, that is the exponent. That is giving us the power of 10 and giving us an idea of what that power of 10 is. The decimals are just the mantissa that were the significant digits from the value of the concentration. So why is the power of 10 a 6 and not a 7 as the exponent shows? So the mantissa value is supposed to occupy the ones place in the concentration. Occupying the tenths place moves the decimal by 1, accounting for that missing digit. All right, so like if you're thinking about it with that 6, that 6th place within that decimal number, because the 7th place is occupied, but it's higher, it's moving up, so as this value increases, this 6th place is what is truly the first power of 10 before we get to our significant digits. All right, so the ones place in our pH represents the power of 10 and where that power of 10 resides. Then the decimal places are the significant figures that come from the mantissa of that decimal number. So now looking at the antilog. So with the antilog, we are going from the pH back to its concentration or the scientific number. So we're going out of the logarithmic scale, going back to the exponential function. This is 10 to the x, which we put that pH in. So it's going to be 10 to the negative 6.987. Remember, we need to have the negative there to make sure that the number is smaller than 1. When we want to, or I can show you, so what we're going to do is we're going to split out that mantissa versus the significant digits versus that power of 10. So really, what we're looking at is 10 to the negative 0.987. This is the mantissa, which is where our sig figs come from. And then we have that 10 to the negative 6. That's that power of 10. Gives us the decimals places. So what happens is this number right here, when you plug this into the antilog, you're going to get 0.103 times 10 to the negative 6, because we want to leave that power of 10 in the exponent function. But because the mantissa has to occupy the ones place, we have to move that decimal 1 place over. And so when we do that, we actually get 1.03 times 10 to the negative 7. So that helps explain why the exponent function is a 6, because when the mantissa is calculated out, it is occupying the 10th place, and therefore we have to go back and put the mantissa back into its ones. So that explains why it's all about the significant digits of the mantissa versus how many decimal places are in the pH, because of the way in which it is set up.